welcome everyone to this physics education seminar. My name is Nalini Nadkarni. I'm the director for the Center for Science and Math Education here at the university. I'm just going to do a real quick introduction about what the center does, and then I'll be turning it over to Jordan Gerton. The Center for Science and Math Education, which is semi-sponsored this event, is really about science and math education. We have 4 parts of our mission. One of them is to improve teacher training in science and math education. A second is to improve undergraduate science education. A third is to increase diversity in math and science. And a fourth is to try to help scientists and mathematicians themselves disseminate math and science to the world, in addition to other scientists. And throughout all of this, we try to base this on research and evaluation to extend what we learn not only to the state of Utah, but also to around the country. So one of the activities that we like to do here at the center is to assist in the dissemination of science and math education at the undergraduate and graduate level. And we bring in speakers, and other faculty who are associated with our center also bring in speakers. And I'd like to also acknowledge Butch Atwood, who's there in the next to the last row seats, who's in the chemistry department. He's an associated researcher and faculty member with the center, and just recently he brought in a very wonderful chemist and chemistry educator. That achieved a lot of interest, and we realized that that was something that really has a place here at the university. So when Jordan approached us about the possibility of co-sponsoring this event, we were all over it. And so I would just like to welcome you on behalf of the center and thank Jordan for bringing Max here today.
Thanks, Nalini. So just briefly, we're really happy and honored to have Matt here. I've known Matt for about 5 years through what's called the Cultural Scholars Program with the Research Corporation for Science Advancement, which basically promotes science education, research in science education, good practices in science education. And Matt gave already a 2-hour seminar this morning in physics. And then we took him to lunch and we pumped him for information for another 2 hours. And he's an incredibly deep well of knowledge, though, on science and physics education. And so we've just basically got just the tip of the iceberg with what we've already found out. And so we're really excited. So Matt's did his undergraduate work at the University of Guelph in Canada, and then did his PhD in particle physics at Princeton University, and eventually made his way to University of Illinois, where he's been a professor there since the early 90s. And he and his physics education research group have been really driving a lot of innovation in particularly the teaching of large lecture courses, particularly related to physics. And I think a lot of the innovations and their research bears on all the sciences. And so I hope that those of you who are not in physics will still be able to come away with something very useful for yourselves in your classes, and maybe a different way of thinking about some things. And so with that, I'll just let Max take it over.
Thanks, Jordan. So far, it's had a wonderful visit. I got to drive around the beautiful scenery and countryside of it yesterday. I came kind of early to that, and you have a beautiful campus and very nice surroundings. Let me start this up. And here we go. So, okay, there we go. All right, so I'm going to tell you about some of the stuff that we've done fairly recently at the University of Illinois in trying to have our students be better prepared for lecture, and the effect it's had on our students and on their learning and on their attitudes. In order to do that, I need to give you a little background on what we've been doing at the university for the past 20 years or so, but I'll do that very quickly at the beginning. So I'm a bit of a latecomer to physics education research. I was doing particle physics and astronomy and stuff like that, and up until basically this year. But I've always loved this stuff, and so I feel like I'm sort of coming out of the closet. This year, finally, I don't have any research grant money in particle physics anymore. It's all switched over to education research. So I've cut the strings behind me, and this is what I'm doing now full time. It's really good. So we have 4 faculty doing this, and a whole bunch of graduate students, and so people that are academic professionals and affiliated in some ways. And so it's a pretty big group. And we have money from the NSF to do this mostly, and also some from Macmillan. We have a very interesting partnership with Macmillan Publishing, which I'll mention to you as I go. All right, so just to set the stage, in physics at Illinois, it's a very big operation. We teach about 4,000 students a year in just our first 2 semesters of introductory physics. And so the stuff I'm going to tell you about today are things that we've done to the first 2 semesters of those. The mechanics is 211, that's sort of Newton's laws, and E&M is 212, that is electricity and magnetism, and a little bit of optics, things like that. So most of these students are not physics majors, they're engineers. We only have about 100 physics majors in these classes in any given semester, and 1,000 engineers. And so it's mostly engineering students, and it's calculus-based stuff. And so it's pretty typical, and by that, what I mean is that there's a lecture, there's discussion, there's labs, traditional exams, nothing too out of the ordinary in these courses. And so I just want to show you how it changed in 1996 at the urging of the College of Engineering, since the courses weren't functioning terribly well before the mid-90s. We essentially decided to align what we were doing with best practices as we knew at the time of how to conduct lectures, how to conduct discussions and labs, and how to disseminate homeworks online. It turns out that Illinois has been doing online learning, computer-based learning since the 60s. Few people realize that, but this thing called Plato and then Novanet was developed there. And the flat panel display was actually built by engineers at Illinois to enable the learning stuff, the computer-based learning, because they needed a screen with a proper refresh rate so you could actually do interacting with the student on a computer. So it was a very long history of this stuff, way before my time. And so we started to do what was in the literature in the early 90s of what people knew about peer instruction and things like that. We decided to adopt that. And we did something else which was very important, which was that we institutionalized the courses. So the course now existed independent of the person teaching it. And so the lectures were there. We had PowerPoint slides. All the discussion problems, everything was essentially there so that anybody could step into these courses and do a good job teaching them. It was a little bit of an uphill battle to get people to buy into that at first, but now that is definitely our culture, and people are extremely glad that that's the way it is. It has big advantages. It means that people don't have to reinvent the course every semester, and it means that people now have time to innovate. And so this really has enabled us to do innovation, and it's also made the courses sustainable. So they really are very similar now to what they were 15 years ago, but I want to try to convince you that they're actually better than they were 15 years ago. Okay, so before we did this flipping, we had a long lecture. We had 1.5 hour lectures. And in the lectures, we did just-in-time teaching and peer instruction. So just-in-time teaching, this JIT thing, was just becoming popular in the 90s. And the idea is that you poll students before class, you see where they are in their learning, then you design your lectures to sort of accommodate for that. And it's not as daunting as it seems, because every semester with 1,000 students, it's the same problems. And so you don't have to change the lectures every time. So once you've done the lectures well once, then you have those in the can. Peer instruction just means the students talk to each other and then answer the question that you ask them. So that's how we do the lectures. Discussions were also group work, and I'll show you a picture of that in a minute, and it involved training of the TAs quite extensively, so that was kind of interesting. I'll show you a little picture of that. Online homework, like I said, we've been doing that for a long time, and we also developed at the time in Illinois something we called interactive examples, which was kind of an online homework tutorial where it's when a student clicked on the help button, instead of the system saying use Newton's laws or something that really don't help, it would be, okay, well, what do you think? You know, it kind of asks them a question, and they're very involved and have several branches, and so depending on how the students answer one question on their way to the final answer, you could go down one path or another, and it would give you feedback. So they're quite involved computer-based questions. And then the labs were pretty typical, and then the exams, we went to multiple choice. And I'm going to say a little about that because it's something that people think is kind of a bad idea, but I want to try to convince you it's a good idea. So discussion sections are interesting because in the mid-90s, I would say 95, we essentially renovated our discussion rooms. So these rooms used to have a blackboard where the TA would solve homework problems, typically. The TAs could sort of do whatever they wanted. And there would be seats facing the blackboard, and students would sit there passively. And then we realized that that wasn't really the way to learn, or we read about better practices. And so now what the students do is we give them fairly hard problems, that they can't just answer immediately. They look at those problems as group of 4. They have a big pads of paper typically, and they have to draw pictures. They have to figure out a strategy for solving the problem. So they discuss it with their partners, and when they get stuck, the TA runs over, like right here. He's running so fast he's blurry. And he's getting to that student who then needs a little help. Maybe he'll ask that student, well, have you drawn a picture yet? Well, what do you think is going on here? Instead of just getting onto the board and saying, well, try multiplying that by this. So that's very important. And the training TAs to do this is hard. In fact, training me to do this is hard. When a student asks you a question, it's very easy to answer it. It's much harder to ask them a question back. So this was a big deal. The exams, we switched to multiple choice for a variety of reasons, not the least of which was that we had typically 1,000 students in the semester, and it's a huge ordeal to grade them, but we realized that we couldn't grade them fairly, and we actually did studies of this, and certain, if you grade a student with a messy handwriting, you tend to grade them lower than people with very neat writing, and then people would complain, and the people who complained would usually get their grade raised by a point or two, and so it was kind of unfair. And so we went to all multiple choice, midterms, 3 midterms and a final. And we came up with a scheme to give sort of partial credit on it, which I won't bore you with. But the thing that's sort of interesting is that we did a pretty thorough study. After years of doing this, we wanted to make sure that it actually was kind of working and that we weren't fooling ourselves. And so we did a study where we essentially looked back at our old exams and we did some statistics to see if they were good exams. And we also watched students take similar exams and interviewed them afterwards and sort of tried hand grading and correlating it with multiple choice. And so I'll just show you the results of that. It's kind of interesting. There's sort of 2 things you can ask. One is, how reliable are your exams? And that the question is really, if you make up 2 different exams, and if you give this one, or if you give the other one, do you get comparable information? In other words, is it fair from semester to semester? So the one way to check that is that you can ask for a given student during the course of the semester, since they take 3 midterms, each one has maybe 25 questions on it, plus a final with 50 questions. There's something like 125 questions that they've answered. You can just break them into odd questions and even questions, and you can grade the odd ones and even ones, compare the score that they would have had if they just did half the exams on one day and half on another or something like that, and just take the difference over the sigma, and you can find that the percent difference is about 3%. So we're consistent. The exams on average tend to give you the same result. That's basically what that tells us. The other thing which is more important is it valid? And so here what you're seeing is for the students that we actually paid to stay a few hours late after the final exam, where we had them bring the final exam in, and for a select bunch of questions, they now had to work out the question on a piece of paper while we watched, explain what they were doing, and we had several people watching and grading these things by hand and coming up with what we would have thought we would have graded their answer to be if this had been a hand-graded exam. And we correlated that score with their multiple choice score, or multiple choice on this axis. This was the average grade given by the people grading and watching, and there's a good correlation. Okay, and so essentially what we came up with here is that ranking the students based on their multiple choice score was consistent with the ranking based on their written answers with a very high confidence level. And so the statistics and everything were in that paper. But it was cool because as a particle physicist, we actually ran a Monte Carlo. We did all kinds of cool things to try to understand the statistics of this thing, and so it's all in the paper. All right, so that's sort of an argument for why multiple choice testing isn't really that lowbrow. I mean, you tend to think that it is, but it's really not that bad. All right, here's a bit of an aside I just want to mention, because one thing that we've been noticing is that students, there's a lot of parts to our course, as I'll show you, and students will in very good faith work hard on all parts of the exam, and they'll still do very badly on, all parts of the course except for the exam, then they'll do badly on the exam. And we're not doing a good job, evidently, of giving them feedback, what they need to study to do better. And students have a bad ability to estimate their own knowledge. So we recently on a test, for example, the last question on the test was estimate how many questions you got wrong on this exam. And the students who did worst on the test were the worst at estimating what they knew on the test. And so it's not surprising, but it does tell you that it's hard to know what you don't know. And so to that effect, what you're showing here is what, in our current courses, we can give them a grade for effort. Okay, so the effort grade is everything but exams. So it's for the homework and things like that, there are parts of the course where you do a lot of work, and eventually you get done with it. And if you've done all that, your effort grade is 1. If you missed a bunch of stuff like that, it's going to be lower. But basically, if you look at the effort grade for students who are doing sort of passing work, which is C- or higher, it's pretty high. The effort grade for students who are failing the course, it's still pretty high, right? So you can ask, for students who have a pretty high effort grade but are failing the course, what can we possibly do to help them? Because they're really trying. They're spending a lot of hours on this stuff. How can we give them better feedback? And so that's basically, if you look at, and this isn't an answer, I'm just showing you this in a slightly different way. If you just look at the students who are passing with an effort grade of 0.8 or higher and are failing, the failing ones are kind of sitting down here. Okay, so they do really bad on exams, but they try really, really hard. And so this is something that we're working on right now, and I don't have an answer for you, but I think it involves having a better measure of what things students understand and what they don't, and giving them feedback before the test. So that's something we're working on really hard. So that's just a little peek. All right. So anyways, before we did the flip, this is the last thing I'll tell you before I'll show you what the flip really was. The course was actually really quite good, so this is supposed to convince you of that. What you're seeing here is good is on the left, which is kind of weird, and bad is on the right. It's an attitude question of the student's attitude towards the course before the course and after they took the course. So the fact that the blue thing before the course is kind of weighted towards the bad side, and the red stuff is weighted towards the good side, means that they came out of the course feeling better about it than when they went in. So that was a vast improvement over the way it was before we did these first innovations 15 years ago. We also have students do these ISIS forms, sort of rank their teachers, and multiple choice forms that the university gets and bases your promotions on and things like that. And so basically we do that for the TAs as well. And after we did the initial set of course revisions, about 80% of our TAs and professors were ranked excellent by the students. In other words, they were in the top 10%. So this is something that a local newspaper does. They dig out all these records because it's public record, and they just publish the names of all the people teaching in the university that were ranked excellent by their students. And so it went from essentially 30% to 80% for the physics teachers. So that was a good thing. So what's the problem? The problem is that students still come to our classes not prepared. And the whole point of this classroom flip, if you're not familiar with what it is you want students to do stuff before they come to class, to encounter the material before they walk in. So you say, well, of course, that's just reading the textbook. I used to do that. And so we asked our students, do you read the textbook? And this was data from before, and they basically did it. They spent $150 to buy a nice, big, fat, heavy textbook that they carry around that probably gives them some sort of back issue, and then they never open it, and then when they sell it back, they lose $50 or something like that. And so it was a bad deal all around, and it's especially bad as a professor because you're in a class now where you would like your students to have seen this stuff so that you can sort of have a common ground and you can have a discussion, but instead you just have to start from square one. And so that's the situation we were in. And we knew that this was the case, by the way, because we've been doing just-in-time teaching for many, many years, and just-in-time teaching is before class, the students were required to get a point, they would have to go online and answer some questions that they should be able to answer if they read the book, right? And they only got participation credit for doing this. We didn't want them to feel bad if they couldn't answer all the questions yet because they hadn't had the lecture, but it told us what they knew and what they didn't know, and we discovered that they didn't know anything they were supposed to know by reading the textbook. And so that was the problem. And so we have a whole new approach to the lecture, and it sort of has three components to it. Two of them are before class. We have these things called pre-lectures. So we don't have a book anymore. We don't make them buy the $150 Tippler. Instead, before every lecture, instead of having the chapter they were supposed to read and reading it, which they didn't do, they now go online to a site we created where these pre-lectures presents the material that they would have read in the book, and it does so in an animated way. So they see an animation and they hear a narration. So it's like a little movie, and it takes about 15 to 20 minutes. They do that first. This is typically done the night before. They can do it up to a week before, but usually it's right before the lecture, which is fine, because then it's fresh in their mind. Then they stay on their computer, it's still the night before, and they do what we call a checkpoint, which are just some conceptual questions, multiple choice, just to see what their knowledge is. And for each one we ask them to explain why you answered A, B, or C. And I'll give you an example, you'll see what I'm talking about. And then in class now, we know that they have seen these things, because we track them and we make them do it. They get points for doing it. And we understand because we read the answers to these questions what they don't understand. And so we know where to focus our attention. And so now the lecture is much more interactive. We have our students using clickers, and we ask them between 5 and 8 questions in a 50-minute lecture. So our lectures are now shorter than they used to be, and we cover more material, and we do so with less lecturing, much more interactive stuff in the classroom. Okay? So, this is all worth 10% of their grade, doing all these things before lecture. So it's not a big number, but it's significant to the students, and it makes them participate. And like I said, we went from having hour-and-a-half lectures twice a week to now having 50-minute lectures twice a week. And we cover more material. All right, so let me show you one of these pre-lectures. Now, I'm not going to have sound, which is unfortunate.
You might, you've got the,
Oh,
it's kind of
yes. That's brilliant, Jordan. Give that nice weight. Okay. So this is, okay. All right. So let's see if this is going to work. In fact, I could probably do the actual lecture. Let's try that. Oh, okay. Okay. So this is what we actually did this semester. Okay, so we'll go as a student, this is what you would see. You would go in here, you would see the whole course kind of laid out, and then you could drill into either one of these sections, and this is the first 6 lectures, deals with linear dynamics, things that you're not perhaps very interested in. At the very end of the semester, we did static fluids, and so a student now would go to the pre-lecture.
We start this lecture with an overview, a plan for what will be presented. In this pre-lecture, we will begin our study of fluids. We will start with a discussion of the origins of pressure in a contained fluid. We will use Newton's second law to determine the relationship between this pressure.
So we don't want to watch the whole thing, but you get the idea here.
We will then use this relationship to obtain Archimedes' principle, the relation between the point force.
So that is essentially a sort of an introductory slide, and then they go through several more of these slides, and I won't do them all. I'm just going to skip over to the one that I want you to see.
Water sitting on a table. The weight of the water.
Oops. And now I'm doing what a bad student would do.
Here we see
Okay. Now, and they can do this, and it's perfectly fine if they do. And they have to answer a question here and there that kind of slows them down, just checks their knowledge before they're allowed to move on and do the rest of the slides. So Archimedes' principle, and finally floating. Here's the one I wanted to show you.
on the last slide, we introduced the buoyant force and examined an example of this force exerted on an object whose density was greater than that of the liquid.
Okay.
What happens if we replace that object by another one whose density is less than that of the liquid? Say, a plastic box. We start by completely submerging such a box in liquid. The weight of the box is now less than the weight of the displaced liquid. Hence, the net force on the box points upward, causing it to rise. Once it reaches the surface, it will.
So Gary gets a little excited when he's narrating these things. But anyways, you get the idea. I won't go through the whole thing. So the student now has watched these slides. The slides typically each introduces, in a couple of these slides, each the concept that we want to do in lecture. It derives in great detail all the equations that they're going to need. So at the end of this slide, it will have been derived this sort of idea. What is the fact that the displaced volume depends on the weight of the object and the density of the liquid and stuff like that, which is what they needed to know for this particular thing. So just to give you an idea, what they had to do. Okay. So let me go back to this. So like I said, for a student to watch all of those things, it would probably take them 20 minutes. And it varies a little bit from pre-lecture to pre-lecture. But it takes the place of the book. This is what we would have hoped they would have read in the book. but now we know they did it because we can check the server logs. And we do. And so anyways, so they do this the night before, instead of reading the book, and it introduces all the concepts that they're going to see in the lecture before they come to class. All right? Now, it's not surprising that the students watch these a lot more than they read the textbook. For one thing, they get a point for doing this out of 1,000. So they don't get a lot, but they do get something. But they do value this stuff, and I'll show you some results to prove that to you in a minute. Okay, let me do a little bit aside because it's interesting how we came up with the right way of doing this. We weren't born knowing how to do this. So basically, if you go to the library, you can read the research that much smarter people have done on multimedia learning, and you can sort of learn how you're supposed to do this. And there's several books on this that sort of tell you how much stuff you can present in a certain amount of time, how much goes in your eyes, how much goes in your ears, how you don't want to overload the brain. There's a cognitive load factor that I'm sure people here who are in psychology know much more about than me. If there's any of you that if I say anything wrong, by the way, if you're in this field, tell me afterwards. All right. So the idea is that you have two channels of input, and it's not surprising. People have known this for a long time. The Air Force knows this. If you have a heads-up display in fighter planes, you want to get a lot of information into your pilot very rapidly. So you have stuff going on here. You have noises. You have tactile things, and so it is definitely true that you can lower the cognitive load on a person as they're learning stuff by having two channels in. And so here's how we kind of learned how to do this. This is an eye tracking station, so there's little lasers that fly out of these windows and bounce off your eyeballs. I guess they're not probably lasers, but there's some sort of optical device that tracks your eye movement, and it can tell exactly where you're looking on the screen. And so we could tell, when we did studies, we would show students slides where nothing was moving and we just had narration, and where certain things were moving and we had different narrations, and we could tell when they were focusing on what we felt was the relevant material and what fraction of the time that we're doing so. And so we kind of learned the hard way how to make these slides that we made. And so, here's just a little research that we did for certain slides. You could get students to focus much more on the relevant part of the slide if you had animations than if you didn't. So the fact that the blue things are higher than the red things is what you're supposed to look at. Right. And if we have time later, I can show you, well actually, it's just kind of interesting how this thing works. This is an example. So, well, the kind of input from this machine. And what you're seeing, if you look at the little blue dot, that is where that person is looking at any given time. So as something changes on the screen, then instantly their eyes are drawn to that. And so here nothing much is changing, but as soon as something appears on the screen, I won't do it again. Here's one where everything is already present on the screen and all they were doing was listening, and their eyes were just all over the place. They were not focusing on anything relevant particularly at all. So it's not surprising that this works. All right. So that's some of the tools we use to learn how to do this. Once we had made the pre-lectures, we wanted to understand it, if we could use them in our own classroom. Before we subjected 1,000 students to it, we wanted to be convinced that it wasn't going to hurt anybody. And so what we did was a clinical study where we had, essentially, we took 32 students, we divided them into two groups of 16, and we had some of them doing the pre-lectures and some of them doing the same exact sections out of the textbook. And they were all required to come and do this while we watched. And so we knew that they were doing it and spending the same amount of time doing this stuff. And so what we did was on day one, they did 2 units from the book, 2 units from the pre-lectures, and they did a test. They did it again. They did a test. And they came back the next day. They did 2 more units, and then we had them back 2 weeks later to see what they remembered. And so when you combine how they did on all these tests, including this retention test, what we found was that they essentially do better and statistically significantly better when they use the pre-lecture as when they did the textbook. In fact, we had a third group, which I'm not even going to really talk about, but that just read the script for the pre-lecture, and they did better. They didn't do as good as the pre-lectures, but they did better than just reading the textbook, which was kind of interesting, because they were shorter in this. I don't know. But basically, there's a pretty big effect that we're not hurting anybody by making them do this. And we can also sort of break it down, blue and red versus how good the student is. So we knew what their score was later in the year when they'd taken their final exam, and so we could just see for their final score, we had a pretty big effect on students that were struggling a little bit in the course, and the effect size is a little smaller for the better students. And we didn't have anybody who did really well who did the textbook, but we had no way of knowing beforehand. It's just the way it worked out. So anyways, this is all published, and you can read about this stuff. So then we were convinced that this stuff was sort of working. So then we used it on our students, and that's the result. That's what you see. Okay, so the other thing we did before class is we asked them these checkpoint questions, and I'll show you quickly what that looks like. The idea there is that, and we've been doing this for about 15 years, by the way. This just-in-time teaching stuff works great, and even if you're not going to do pre-lectures, even if you're not going to flip your classroom, there's no reason not to do this, because the WebCT or whatever you're using makes this easy. So it's not that big of a deal. So you ask some questions before class, and then you look at it before you finish your lecture the next morning. And it actually gives very good buy-in for students if they have a little bit invested in the material that you're going to see. This increased attendance in the lecture even before we have the pre-lectures and so on. All right, so here's an example of a question. I don't want to dwell on it, but it's a fun physics question for those of you. How many here are in physics? Okay, so not that many. So it's a full glass of water, and there's an ice cube floating in it, and the bunch of the ice is sticking out of the water because the ice is less dense than water. So the question is, when that ice melts, what happens? Does the water spill out of the glass, or doesn't it spill out of the glass? It's an interesting question, right? And the answer is it doesn't move. It stays unchanged. But the students don't know that, so we ask them to say, does it spill, does it go down, or does it stay unchanged? And down here, it's very important, there's a text box where they explain why their answer is what it is. And they're graded, by the way. You don't have to get this right to get their point for this. It's just participation, right? You just want them to do something before class. And we see here that half of them got it right, but the other half got it wrong, A or B or these two things. And so we can ask, for the students that got the wrong answer here, it's easy to just go in and see what their explanations were. So here's their explanations. And it's pretty great. I just want to draw your attention to this one. Right? So I like this so much, that's why I stuck it in here. And so these are all the good explanations for the wrong answer, okay? And so in the lecture now, this is what you do. So this slide is from the very lecture that we gave. This was only like 2 weeks ago. And so we reiterated this question because half of them had got it wrong. So this is a great learning moment. And I cut and pasted in explanations that they had given if they said A, B, or C. And remember, C is right. So this is the correct explanation at the bottom. But I got to put that one in there, and people thought that was pretty fun. And then we can have a discussion, and I can show them this is how you did last night. And then they vote using their clickers, and then this is how they do in class. Okay, so suddenly it goes from half of them to 80% of them get the right answer. Right? And then people also ask questions like this. Well, if this happens, it doesn't go up, and why do I care if the ice caps melt and things? So it's a very good question. The answer is that a lot of the ice is sitting on land, and the water would run into the ocean. All right, and then you can ask other questions that are related, which I won't bore you with, but this is how you can now kind of tailor your lecture to go along with the stuff that they saw before the lecture. Okay, and so that's really what we do. And so we have a lot of these clicker questions in class, at least 5, sometimes 7 or 8 or 9 in a lecture. Okay. All right, so the peer instruction has been around for a while too. Eric Mazur at Harvard sort of coined that phrase, and he's been doing this for a long time, and so we basically copied him, but it really does work. So let me show you, I got to give props. This is, some students at Illinois invented this thing. So if you're in a big room, and somebody asks a question, first of all, I'm half deaf, so I can't hear you. The other students can't hear you, and if you're trying to record the lecture, nobody can hear you on the recording. So these guys have this little, it's like a Nerf ball with a microphone in it, okay? So I have this thing in my hand, it fits perfectly in one hand. Student raises their hand, I just whip it over to them, they catch it, they push the green button, and they ask a question, and they whip it back, and they think it's great. So look for my ball, I'm hoping they get their little business going. I don't know if they will or not. All right, we'll skip over this. Actually, I won't skip over this, this is one of my favorite things. So at the end of before every lecture, we ask them a very open-ended question, which is, what do you think we should discuss in class? Right? Is there anything that you found particularly confusing? And students will write almost anything in here in the hopes that I'll display it on the PowerPoint slide. A lot of students tell, you can tell when they're upset about cross products and processing gyroscopes, things that are really hard for them. But sometimes they'll just write anything. This was the night of an exam, so they were doing this the same night. They had a big high-stress exam, and the student wrote this. This seems okay, but honestly, I didn't really watch it closely. I contemplated not watching it at all, where it being the pre-lecture. Okay? I'm using one of the freebies, and what they mean by that is, in order to make this low stress, we essentially let them forget to do it 3 times, and it doesn't hurt them at all. So we don't want this to cause any stress. But I hate going to lecture without an idea of what we're talking about. Right? How great is that? So that totally made my day. So now let me show you some research data that shows this is actually helping our students. So now basically the flipping is we've given the material before class, they come to class, in the class now we have a much bigger give and take. The students know the answers to the questions. And I taught for years the other way, and the difference in the attitudes and the engagement of the students now is like night and day. It's really amazing how coming to class and knowing a little bit about what I'm talking about makes them much more prone to get involved in the discussion. At least for me, it worked really great. All right, so these checkpoint questions, this particular question isn't important. The point is we have hundreds of these questions that they do before lecture during the semester. And so this is just a typical one. And it doesn't matter what the question is, it doesn't matter what the answer is, but from semester to semester, about the same number of people get this one right. All right, about 60% of the students. So if I just look at, for spring 06 and spring 07, which were 2 semesters before we did the flip, okay? And I just plot on this plot for this one question that we asked them. I said, 0.57 is one and 0.56 was the other one. I get a point here with error bars on it that lays along a line that has a slope of 1. They would lay exactly on that line if every single, if the question would have the same exact fraction of students getting it right in both semesters. Okay. Now we have hundreds of these questions. So if we now add, oh no, I'm getting ahead of myself. If I do that now, comparing this answer from spring 06, in fact we average spring 06 and spring 07 for this axis, since the things are the same. And now after we flipped the lecture, a lot of students got this one. More students got it right than before. So the fact that this thing is above the line tells you that doing this flip for this one question was a good thing. All right. Now maybe it's because that exact question was described and it was like cheating. We don't know, but we can actually look at all the hundreds of pre-lecture or checkpoint problems, and you see before everything lays right on the line. That means that every semester beforehand nothing really changed, and suddenly now more students are getting this one right, or getting all of these questions right. The fact that all these guys are above the red line means that more students are getting the concepts than before. Okay, so that's a very good thing. Then we have some other interesting data, because what I did when I showed you this thing, remember what I did? I clicked on one and it started to talk, and I went to the next one. I could basically go through one of these pre-lectures in 2 minutes, or probably even less if I wanted to. So if I was a student and I didn't feel like playing along, I could seem like I was playing along, and all the time I wasn't. But we can catch them because we keep track in our server logs of how much time they spent on each slide, and we can just accumulate that very easily and see how much time they spent on the whole pre-lecture. And so for this one pre-lecture, for example, there's a peak of students that obviously didn't do it. And then there's another district peak here, and a tail off of the amount of time the students spent on it. So for this particular pre-lecture, about 14 minutes was the time. If you watched every single slide all the way through, it would take you this long. And then students could stop it and replay it, and so some students spend just more time on it. Okay? And so we just sort of divided the students into 2 groups. Ones who didn't play along, we'll call them non-viewers, and ones who played nice, we'll call them viewers. And now I'm going to take that scatter plot that I just showed you and break it into non-viewers and viewers. And so what you see here is that for the people that just sort of skip through it, their performance on those conceptual questions is now exactly the same as what it was the semester before we did any of this stuff, right? And now when we remove those people from the average, then now you have an even bigger effect on conceptual knowledge for people who actually played the game and get this right, okay? Now, you could say, well, these are just students who are more likely to take courses more seriously and everything else. So it's, whenever you have humans involved, it's very hard to make concrete, absolute statements. But here, I can certainly say that on these questions, these students did better. All right, here we break it into sort of student ability. So for A level, B level, and C level students, I'm just showing you the same plot. So for weaker students, middle students, or high performing students, it helps to do this. All right, so flipping the classroom has a real advantage. This was just to convince you that nothing else changed between the 2 semesters. The same people teaching the course. We actually introduced more materials and so on. So it wasn't like suddenly you had a heroic teacher who was doing everything right in the semester before we didn't. Okay, so let's, I'll skip over the comments since I don't want to run out of time and just show you some more. Maybe I won't skip over. All right, so you do see this all the time. It takes some students a while to realize that there's value in these. And then they kind of, once they realize it though, then they start to take them pretty seriously. Okay, so here is some interesting stuff. Course difficulty, so these are all the semesters now before we did the flip. And what we ask them every semester, at the end of the semester, is we ask them how difficult was the course. And they have 5 choices: very difficult, somewhat difficult, sort of neutral, somewhat easy, really easy. Okay, and if they answer difficult or very difficult, then we put them in this category. So it used to be that 80% of our students thought the course was difficult, and after the flip, it was almost half. Right. So the perception now, the material didn't change. We covered the same material. In fact, we covered more material, but the perception of the student changed toward the material. Right. Same material, same teachers. Students now feel differently about it, which is huge for us. So that's the same thing I just showed you. Attitude towards the course went the other way. It went from being kind of not very positive. So here, about 40% of the students had a positive attitude toward the course at the end of it. After this flip, it went up to about 70%. Right? So that's pretty good. And my favorite is this one, the value of the lecture. Because here you might worry that giving them the stuff before class, suddenly they wouldn't even see a value in the lecture anymore. And so the lecture was valuable to about 40% of the students before we did this. Afterwards, it almost doubled. Right? So that's one that's really, really important. So if students come to class and they find your teaching now more valuable than before, then that's a very important thing. For me, this was the neatest result of everything that I've shown. And so I think that's really cool. And we did not, this is not attendance or anything, right? So they come for a point. I mean, so you would argue that, well, they're just coming because they have to. No, this is their survey results. And if they came just because you were taking attendance and had no value in the lecture, they would slam you on this question. They would give 0. They are not shy about telling you exactly what they think. Okay, so let's see here. Oh yeah, exam performance. We did some studies of this, and then I'll wrap it up. So how does doing this change performance on exams? So this is a little harder to do because you would have to give them the exact same exam, right? And so, but we do have some old exams that we haven't used in a long, long time. So we pulled one of these out for a midterm from fall of 1998, a long, long time ago, compared to the fall 10 years later. And so you see that it's not a huge improvement, but it is an improvement. It's certainly not any worse. So these are basically, each dot here is a question on the exam, and this is how they did on the exam in fall a long time ago, and after we implemented these things. And so you can do statistics on this, and you can find the average, and they do, you know, it's a bit better 10 years later after we do the flip. Okay? On final exams, you can do the same thing. We give 2 final exams, and so on one of them, there was a bigger effect than on the other one, and we were kind of interested in this stuff, because there was a couple of questions here that were really, really low, they did a lot worse now. And there was a couple of topics that we removed. And I think one of them was, it was pointed out was power, right? And another one was transformers in some really detailed way because people weren't getting anything out of it. So this exam had a couple of questions on it that we actually didn't cover anymore. So these really low ones, so that was kind of an unfair exam, I admit. But even if you include those, we didn't do any worse. So here we're comparing one fall to the other, so it went up a little bit, but it's not that significant. So then you can ask, well, exam performance, why didn't it get a lot better like these other things? And part of the reason is that the exam has conceptual problems on it, but also a lot of calculational problems. And students have a finite amount of time to study for their you know, they have 18 hours of classes, and they sort of study as much as they think they need to. So you could actually dream up scenarios where they would do worse on the final because they're feeling so good about the course now that they know, I don't need to study, I'm doing really great. And you know, I mean, so it's harder to see, to expect a really big effect on the final. So maybe I'm rationalizing here, but this doesn't depress me. The fact that we did something totally different and we didn't wreck the place was important to us.
Did you, this survey that you pulled all this data about attitudes and stuff, and time spent on different aspects of the course, did you give that to them before you flipped the class?
Yes.
So do you know whether they're spending less time now on all elements of the course, or more, or, I mean, is there a difference?
I would love to know if they're spending more or less time studying for finals, and I don't think that's one of the questions, I don't think that's easy for us to know.
What about all the other aspects of the course? I mean, just sum up how many hours per week they spend.
I'd say they spend probably, on the pre-lectures and the checkpoints, probably before every lecture it's like a half an hour. So those things combined, so maybe an hour a week. And on average, the students tell us they spend a lot of time on homework, so I'm going to say probably 3, 4, 5 hours. I mean, I'm sure there's a distribution, but they do a lot of work in this course. And so I don't know how much of that is really spent studying for finals, so but it's a really good question, and we should try to get some more data on that. So, actually, let me just stop and give you sort of my key messages. I can talk forever, but I won't. So all the stuff that we did was sort of enabled by this initial restructuring that we did early on. So I can't emphasize enough how important that was for all the things that followed. So the things we've done in Illinois over the year, including the very existence of this education research group, really was made possible by the fact that these courses became departmentally institutionalized in the middle 90s. Before that, it was just a free-for-all. You were assigned to teach the course, and then you had to do everything, and it wasn't a fun experience, and then you never wanted to do it again. And then the next person's turn was to do it, and it wasn't good. Borrowing from other people made this possible, right? So we borrowed everything we could when we did this, which was a very important thing to do. And we're pretty excited about the impact it's had on our courses, and we're working on more things. And one of them is understanding how to prepare students for exam. We're doing some stuff with labs. And something that I didn't talk about at all, which is adaptive testing, which is a system where you give a student some questions to see how they do. If they do them really well, then you give them some harder questions to see how hard you can push them. If they don't do very well, you ease back a little bit, and you sort of tailor their tutoring to their ability, in a sense. So that's something we're working on. And with that, I'll just stop talking, and if you have questions, I can probably find a slide to answer. Yes, sir.
So one of the things we try to do is not to make the exams exactly like practice problems that the students have had, because we want their understanding to transfer, not just the ability to jump through certain hoops.
Right.
So I'm just wondering, in your case, when you gave them these conceptual questions, how close were those questions to the ones that they've been practicing on throughout the semester?
The conceptual, well, okay, so the ones that I showed you, those scatter plots,
Yes.
those were all the conceptual questions that the same ones that we had been using semester after semester. They were the same ones. And those were little assessments that we gave them before every lecture. So it is essentially gauging their understanding of the material before they've seen it in class.
Yeah, on the exams,
Yes.
were those questions the same as the ones you've been
No,
asking?
no, no. No, the exam questions were not, I mean, some might be very similar. I mean, honestly, in physics, there's not that many different things you can do. And so, I mean, the students would think they were completely different. If you had a ramp like this, and you had a ramp like this, and one had a ball and one had a a cylinder on it, some students might think these are completely different. Some students who had learned physics and were a little more sophisticated in their knowledge would say, oh yes, it's the same thing. And it's when you think it's the same thing, that's when you really understand the material, right? And so in a way, that's the sort of stuff you want to learn, but the questions that they were tested with were not the same as other questions they'd seen, but they were of course very similar. They have to be.
In your measurement of effort that you had earlier in the
yes.
slide, and you had the, you know, the D plus or below the failing group,
Yes.
saying they put in a lot of effort.
Yep.
How did you measure effort? Because it's interesting to me what a D plus student thinks effort is, say, versus.
Well, okay, so I'm sure what that measure is what they would call effort. So it essentially is, did they do all the homework? It is basically their grade on homework and on parts of the course where by just working at it, you can get full credit or almost full credit. So homework is one of those things. So they have a certain deadline for their homework problems. Even though it may take them 4 or 5 hours to do this, they can answer the question over and over and over until they get it right, and they get feedback when they get it wrong. Sometimes feedback tells them, maybe try this or maybe try that. So eventually, they will get to the right answer. So these are more exercises than anything else. So they go through a lot of exercises, a lot of practice, spend an awful lot of time doing that. So that's what the effort grade really is measuring. And then the exam grade is, how does that pay off for your performance in the exams? Yes?
You've really presented some fascinating data and results, especially for student performance. And I'm wondering if you could advise us on the impacts on the faculty, especially faculty who are used to teaching the way they have been for years and years, and who we don't maybe have the kind of dedicated sort of science education parcel of faculty. So how would you advise us here at University of Utah to institute things like this when we might not have that in our culture in terms of changing over?
And in fact, every faculty wants to do a good job teaching, every person I've ever talked to. And so when we first introduced, not so much the flipping part, because now doing stuff like that is just part of our culture in Illinois. So now it's not hard to get people to do different stuff anymore. Back in the mid-90s, it was harder. And there, the big change was just institutionalizing the course, starting with the same lectures every semester, starting with the same discussion problems every semester. So basically now, you are the king of your research group, but now when you come into this course, you're not king anymore, right? And so a lot of people resisted that. And they said, I don't want to teach in this course, because I want to do things my way. And so we said, all right, that's fine. And some people have never taught in these courses. I would say 2/3 or 3/4 of our faculty have now taught very happily in these courses, but there's still a few people that don't want to. But what you can do though is you can take the stuff that's there, and now you're free to make changes as long as they're little changes. So you can decide you want to add a slide on Stirling engines when we're doing thermal, or you can decide you want to do something a little different, or you're free to make it yours. You just can't change a whole lot. So that's how we got buy-in at the beginning. And so most people sort of grudgingly bought into that. Yeah, fine, but I'm not going to like it. And then we found that people did like it because even though they could change stuff, they just didn't because they realized, first of all, it's pretty good. I don't have to spend all weekend writing lectures now. I can actually spend time with my grad students. I can get my research done and teach in these big courses. It's not like it used to be. Wow, this is great. And then it kind of became institutionalized just because more and more people bought into it, and the other people would hear, talking over coffee, oh, you're teaching mechanics. Yeah, it's great. And so now it's a very popular thing to teach. We throw our brand new assistant professors into these courses. And that has a real advantage, by the way, because what happens is, since we really stress sort of best practices and doing things the way people have discovered are really good ways to teach, after they teach in these courses for a few years and they go on to teach more advanced classes in whatever it is, quantum mechanics or E&M, whatever, they'll take these methods with them. So we do these checkpoints now in our advanced courses. We do a lot of this stuff in other classes as well, just because people want to.
Yeah, I'd like to follow up that comment because it seemed to me that one of the outcomes that's appropriate is independent of the students and their performance. and it has to do with the faculty and their use of time and efficiency. I don't, from what you presented, know how to balance the investment for restructuring a big program, which takes a lot of energy and work, and the benefits that follow thereafter from the enhanced efficiency associated with teaching. But I have a question to ask. So, you showed the good correlation with an R value of about 0.91, I think, of the evaluation of students' performance with the multiple choice questions.
Yes.
I was thinking while you presented this, that the only result you could have presented to me that would surprise me would be the absence of a correlation.
Yes.
I mean, after all, these are two different ways of looking at the same phenomenon, and the only surprise would be that they're not correlated. So, do you have a sense of whether the multiple choice or the manual evaluation by the observers led to different outcomes for the students? In other words, how many students might have failed in one technique but passed in another? How many would have had a change in grade? The reason I ask this is we do something quite similar, use adaptive protocols for medical decision making. And have wrestled with exactly the same problems. How do you get people to accept a standardized process in the Deming construct of standardization process?
So what we found, it's a really good question, and what we found was the uncertainty, the difference in their grades, the standard deviation of that, when all was said and done, was less than 1 grade band. So like, it wouldn't on average have moved you from a B to a B plus, or a B to a B minus. But for some students, of course, you know, there's always a tail to any distribution, but the standard deviation, the width of that thing was that it wouldn't. So, but the thing that we've learned, which is actually really interesting to me, is that doing multiple choice, you can actually test the question itself. Because you can look at a student performance, not only can you see how difficult the question is by looking at the average, but you can correlate the student's performance on that one question to their, let's say, the performance on the whole semester. And you can see how good that one question is at discriminating what a student's knowledge is. And you'd be surprised that you find some of the questions that you have that are just crappy, in that students always get, the range of grades that students get on it is very small, independent on if it's a good student or a struggling student. And so what you now have the ability to do is to test yourself. So now you can become better at making tests, right? It's very hard to do analyses like that, or it's not, it probably you could, but we never did for graded by hand questions. But now you have these enormous statistics, and you can cut them and slice them and do what you want with them. And so it's a really great opportunity for us to improve our skills at making exams, I think. So that's what I'm most excited about. I'm sorry, I'm really getting bad at picking people's, so I'm just going to start.
This is sort of a twofold question. One is sort of how much of this can you use as an individual teacher without a standardized course and without the time to make 30-minute pre-lectures? What can you do in your class to use these ideas, and what kind of benefits do you think? Do you think you get proportional benefits for using parts of the idea?
Ta-da! There's somebody right here who can answer that question.
So I teach electromagnetics the same way, but I did not have time to do the big fancy animated things, so I record my lectures on a tablet PC with a microphone. So you see me writing as if I were writing on the board, and you hear me talking. I don't have the fancy animations. It takes me about an hour to produce one of my lectures, which is actually about 20 minutes of content. It's what would have been in an hour's worth a day. It seems to work great. They're up on YouTube. The students are using them. I'm getting about the same number of students watching mine as his, and I don't even have the fancy quizzes in there too. The students learn really fast that the lectures help them. I do not lecture in class. There's no lecture in class. The lecture is all outside of class, and I actually do homework in class. I don't do homework like we do homework. I start with, here's homework to do in class, and everybody starts working on it kind of with their buddies around them. And then when they notice that they've got a problem, they raise it. We stop. It's always one of the hard questions, because everybody else has helped them with the easy ones. And then we can talk about that just-in-time learning in class. So this is a very abbreviated, very inexpensive, very low time for faculty expense. and it has saved me bundles of hours. I don't know if you know, I'm the Associate Vice President for Research, and none of the other Associate Vice Presidents teach, because you can't. But this makes it so, don't tell everyone, I can walk into class pretty much cold and be able to carry on a perfectly sensible day for the most part. So I think everyone should be teaching this way. I've never gone back. There will not be a lecture in my class.
And what you're doing is really the real flip, if you sort of define what flip is, where you don't really have lectures at all anymore. So I guess we did sort of a half flip. So we